Let's begin with a basic question. If we already have fast I/O buffers like CML in 30s, then what's at 10 gigabit per second and beyond? Why are we still using LVDS? Isn't it outdated? Not really. Even though LVDS is slower, it's still critical in real-world systems, especially in cars, industrial machines, medical devices, and older protocols. It's simple, robust, uses little power, and is easy to design. More importantly, many standards still require it. So today, we explore why LVDS is still needed, how it compares to CML, and when it's the right choice, even in modern designs. Let's start with the most direct reason why LVDS is still important. Standards. Protocol like HDMI, LVD link, JESD 204A, and camera link were built around LVDS electrical specs. They expect a differential swing around 250 to 450 mV, a common mode of about 1.2 volt, and DC coupling. If you replace LVDS with CML in these systems, it doesn't meet those expectations. CML usually has a higher swing and needs AC coupling, which breaks protocol rules. So, right away, LVDS isn't just a nice to have. It's required by many widely used standards. A big reason LVDS works so well in these systems is because it supports DC coupling. That means you can connect devices directly without extra capacitance or biasing tricks. This is critical in systems like HDMI where DC coupling is needed. On the flip side, CML often needs AC coupling to avoid voltage mismatches, which adds more components and complexity. So, LVDS keeps things simple when you need clean, direct chip-to-chip connections. Next, let's talk about power. LVDS is very power efficient at moderate speeds, say 100 megabit per second to 2 gigabit per second. It runs with a fixed small current and a low voltage swing, using only 8 to 12 milliwatt per lane. CML, however, is optimized for higher speed and still pulls more current and swing, even at lower rates. So, if you are not pushing multi-gigabit per second speeds, CML ends up wasting power. That's why LVDS is often a better option for energy efficient systems like automotive or portable devices. Now, let's cover EMI, electromagnetic interference. Fast signals or big voltage swings can radiate noise and disturb nearby circuits. This is a big deal in cars, hospitals, or airplanes. LVDS avoid that by using small swings, slow control edges, and balanced differential currents, which cancel out the noise. It's a naturally quiet interference. CML is also differential, but its large swing and faster transition tends to cause more EMI unless carefully managed. So, if you want to pass EMI test or avoid disturbing other parts of your system, LVDS is the safer bet. Dual systems are not perfect. Sometimes chips are on different power rails, turn on at different times, or there are noise on the ground. LVDS handles all of that well. It tolerates mismatched grounds on power receivers and idle links. It even includes fail-safe feature to detect when the line is quiet. CMOS is more sensitive. It needs tighter voltage matching and doesn't handle idle or open lines reliably. So, for mixed voltage systems over anything with unpredictable startup behavior, LVDS is more robust. Another strength of LVDS is how widely supported it is. It's built into nearby every FPGA, ADC, DAC, or image sensor. You don't need special SerDes or custom logic to use it. It just works with standard I/O. CML is usually tied to dedicated high-speed lanes and are limited and power-hungry. LVDS give you flexibility, compatibility, and vendor independence, which means designs are faster to build and easier to use. Some protocols don't just prefer LVDS, they absolutely require it. HMI, LPD-Link, and JEST2048 all define exactly electrical spec based on LVDS. If you try to use CML, you'll violate the spec, even if the signal looks okay. That leads to interoperability problems and failed compliance tests. So again, LVDS is an option here. It's the only correct choice. From a cost and manufacturing perspective, LVDS also wins. It's simple to implement. Just a 100 ohm resistors and you're done. No internal termination or complex tuning required. CML, on the other hand, needs careful layout, match terminations, and more components in high-volume production than automotive or displays. That difference adds up. LVDS keeps the bill of material cost low and design easier to manufacturers. Here are the summarized images showing you why CML is great for ultra high-speed links. But LVDS is still essential in many systems. It supports the standards, saves power, avoids EMI, supports DC coupling, enables flexible technologies, and works across a wide range of chips and vendors. It's also easy to debug and cheap to implement. That's why it's still used in automotive, industrial machines, medical, and display systems. Not because it's old, but because it works and works well for a long time. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and please share your comments down below. Lastly, please share the video link with the people who may be benefiting from it.